proposition. The first one, a norm. A norm is a continuous map. A norm is a continuous map. Now, continuous map on a vector space. Continuous map on a vector space. Now, what we mean by this, i.e., if a sequence converges to x as n goes to infinity, comma, then this should also converge to x as n goes to infinity. Converge to the norm of x. So this is what we mean by saying that a norm is a continuous map. If I have a sequence which is convergent within a normed space, let me say, now here this thing is missing something. If I let x be a normed space, if x is a normed space and I have a convergent sequence in x, now what it means for the norm to be a continuous map, if this sequence converges to x as n goes to infinity, then the norm with respect to that sequence should also converge to the norm of x as n goes to infinity. Now we are going to prove this statement. Proof of the statement. Proof. Now we are going to start with what we have and use that to get what we don't have. Now if this sequence here converges to x as n goes to infinity, comma, this implies that this norm here goes to 0 as n goes to infinity. That's what I'm having. So if that sequence is convergent, then that means that this absolute difference here with respect to the norm goes to 0 as n goes to infinity. Now we want to show that this converges to the norm. So in simple terms, we want to show that x, we show that xn goes to x as n approaches infinity. We show that this sequence here goes to the norm of x as n approaches infinity, i.e., given epsilon greater than 0, comma, there exists a natural number n such that this absolute difference here goes to 0 whenever n is greater or equal to capital N. Now let's consider this absolute difference. Now I want to show that this absolute difference here goes to 0 as n grows. That's what I want to prove. Now there is an important proposition which I proved in the previous sessions. This is strictly less or equal to this. Strictly less or equal to that. Kindly, if you don't know how to prove this, revisit the previous sessions. We proved that important proposition. Now, if this is less or equal to the norm of xn minus x, and we know that this goes to 0, so this goes to 0 as n goes to infinity. So this should imply that xn minus x, this should also go to 0 as n approaches to infinity. So this implies that xn norm converges to x as n goes to infinity. Now we are done. We are going to prove another important property. So this proof shows that the norm is a continuous map. We've been able to show that given a sequence which is convergent within a normed space, we can extend this, and we are able to show that the norm with respect to this sequence also converges to the norm with respect to that limit. Yes. Now we have another important proposition.